I'll get us kicked off here. We're going to talk a lot today about 3D printers in terms of implementation on our campuses and higher education specifically. And Dr. Black's really going to go more specifically into the more of the content with the research that goes behind a lot of the emissions and sort of the unhealthy factors that are a part of 3D printers that I'm sure most of you guys in higher education are all aware of. So with that being said, my own introduction, my name is Ryan Lisk, for those of you that don't know me, and obviously the Director of Biological and Chemical Safety here at UT Southwestern Medical Center in Dallas. Previous to that, for almost 13 years, I was at Georgia Tech, working in both the environmental group there as well as the lab and chemical safety group there. And of course, I am the co-chair this year of the Professional Development Committee for CSHEMA. And with that, I will turn it over to Dr. Black so she can introduce herself.
Thank you, Ryan. So I'm Marilyn Black. I am with the Chemical Insights Research Institute of Underwriters Laboratories. And we are a not-for-profit research institute really focused on doing research on emerging issues that impact public health. And we have a specific interest in looking at chemical, particle, air pollution exposure and how that affects folks and what we can do to minimize our risk. So thank you. We're happy to be here today and share with you some of our lessons learned on 3D printing.
Awesome. Thank you. And yeah, Dr. Black and I were able to be lucky enough to kind of get connected with one another back when I was in Georgia. And certainly that's where at least one facet of their research and chemical insights under Underwriters Laboratories specifically was based out of. So her and I got a chance to meet a lot there pre-pandemic and while I was still at Georgia Tech. And it's awesome that it's kind of culminated in the fact that we've been able to do this presentation together. In any event, getting into the meat of that, certainly, kind of going over the learning objectives here for you. I'm sure most of you all can identify a lot of this stuff for yourself, so I don't want to read this word for word, but again, what I talked about at the very beginning is we want to talk about more of the specific stuff that Dr. Black has a lot of expertise in terms of a lot of the research that's been done about impact to human health and air quality with the addition of 3D printers everywhere. She'll go into some of the basics about 3D printing technologies and sort of why they present some of these unique challenges for us. And certainly the different types of feedstock and things like that are all involved in the size of the printer and all these various factors that go into, what ultimately culminates in 3D printer emissions and why we should be concerned about them. And then what I'll talk more about really is more about, at least from the higher education perspective, my involvement previously at Georgia Tech, as well as so to some extent we'll be here, not quite yet, but what we do in terms of assessing impacts on human health and working with our facilities teams, our researchers that are using 3D printers, et cetera, and trying to figure out what those appropriate mitigation strategies will be. So on the agenda for today, largely it's going to be Dr. Black for the first, I would say 2/3 of it, roughly half to 2/3, and then I'll jump in. So she's going to cover again kind of that background information about why does this really matter specifically in higher education, of all the overview stuff I talked about, some of their research findings, and then the understandings that have come out of that. And then I'll talk a little bit more about the implementation in the higher education setting specifically and what we've done previously to try to make sure that we're mitigating those concerns that we have from a human health and indoor air quality standpoint. So with that, I will hand it over to Dr. Black.
Thank you, Ryan. So I imagine that most of you know that indoor air quality is extremely important because we all spend at least 90% of our time indoors, whether we're in our home or in our school, in our office, but we are breathing that indoor air at all times. And indoor air quality is responsible, well, air pollution overall is responsible for about 7 million deaths on a global basis. And out of those 7 million, probably close to 3 million can be attributed very specifically to indoor air quality. But indoor air quality is a public risk. It affects, it can cause both acute and chronic health concerns, but it also affects our productivity and our well-being overall. And one thing we have to keep in mind is that as folks, we breathe a lot of air, and most of that air that we breathe is comprised of many chemicals and particles. And about 75% of the environmental pollution that we do get comes from the air we breathe, not necessarily the food we eat or the water that we drink, but from the air that we breathe. So poor indoor air quality can definitely affect our physical health, We know that it's associated with increasing asthma, respiratory disease. We know from numerous research studies that it produces more absentee situations, and not only in educational environments, but also work environments, that we have less productivity among employees, and it can also affect learning opportunity. So some of those studies show that, because of indoor air quality is affected by a number of things, we know that ventilation is a key component. And some of those studies have shown that if we increase ventilation, we can increase performance of people, but we can also reduce the prevalence of sick leave associated with indoor air quality by about 10%. So the data is out there. It's been studied for a number of years. I got involved with this at Georgia Tech back in the 1990s, and we learned a lot that we're now applying now to this particular issue. So on the next slide, the effects of poor indoor air quality are pretty well established. I spoke to a couple of these earlier, but we know that in educational environments, we see higher absenteeism, increased respiratory concerns. We see a lot of irritation type symptoms, especially headaches, nose, throat irritation. We see lower productivity, lower student motivation, and in some cases, we've actually measured lower test scores and documented slower learning around folks that are exposed to poor indoor air quality. And last but not least, we know that poor indoor air quality leads to increased medical cost. So higher education across the United States, we know that there are many students enrolled, roughly around 20 million, and around 4 million staff and faculty. All of those people are in a situation where they can be affected by indoor air quality if it does exist in their higher educational environment. So how do we manage indoor air quality? As I said, we've studied this for a number of years, and we know that there are 4 major components that if we pay attention to these and manage these, that we can control indoor air quality. It's ventilation in our buildings, it's having good moisture control, it's having good and continuous cleaning practices, and last but not least, it's important to manage good source control so that we don't bring in pollution sources into our buildings. Really, out of all of those, the most effective way to minimize exposure to air pollution in the indoor environment is to prevent the emissions from happening in the first place. So controlling those sources that we bring in or things that we operate that can generate sources of pollution, the most effective thing. So what are some of the more common sources? Well, we know that building materials and finishes are significant sources, especially of chemicals such as volatile organic chemicals or VOCs. Plastic products, packaging, cleaners, disinfectants, and office equipment such as copiers, printers, and new technologies that are developing. And that's one of the topics for this particular activity, is to talk about one of those new technologies that we've been studying, which is 3D printing. And 3D printing obviously has impacted our educational environment significantly. 3D printing brings a lot of very positive attributes for learning and creativity, but it also has some unintentional consequences that we'll talk about. So how do 3D printers work? Well, there are different types of 3D printers. The most common one that we deal with, and one we'll be talking a lot about, is what we call fused filament fabrication, which actually extrudes a polymer or plastic that's heated, extrudes it into putting layers down to form an object. However, fused filament fabrication is just one sort of technology available. There are other types of 3D printers, and we're starting to see more of these in the higher educational situations because of the opportunities to create models and simulate manufacturing, et cetera. And these are some of them that Some of them use metals, so we have an opportunity for metal exposure that might occur. Some of them use powders, such as powder bed fusion. We have an opportunity for dust exposure. We have things like that photopolymerization, which actually use UV light and other sorts of chemicals that can be irritating and sensitizing. And so we have to keep that in mind, depending on the type of 3D printer. You can have different types of hazard exposures. But today we will talk about the fused filament fabrication primarily, since it is so prolific in the schools that involves a polymer or material extrusion process. So what are some of the hazards associated with all of these different technologies? For primarily the inhalation and dermal exposure to the volatile organic compounds, semi-volatile organics, particles, including ultrafine particles or very small particles that can be released during the use of these, carbon nanotubes and certain types of materials, powders. And when you get to some that use UV light or lasers, we have the concern from risk associated with that use. And obviously they all produce temperatures elevated to a point where they can produce a human hazard. So engineering controls are very important to understand these particular concerns and make sure we take the right approaches to protect ourselves as well as observers of this process. So how does a fused filament fabricator type of 3D printing work? Well, very simply, you have a filament that's usually a plastic polymer type material that's heated up and fed to an extruder. It's heated and then it fed to the extruder, and the nozzle of the extruder sends it out according to the print commands, and the melted material is deposited in layers on a print bed to produce the product. It's a fairly simple process. There are a number of filaments in the marketplace, but these two are the primary ones that we see in the educational environment. Acrylonitrile butadiene styrene, commonly known as ABS, PLA, polylactic acid. Those are the most common ones, although you'll see others such as polyvinyl alcohol, nylon, and some polyethylene type materials. So what about the impact of 3D printers when these things operate? Well, obviously, when they operate and these polymers are getting hot, what sort of exposure do they produce kind of as an unintended consequence? And this has been kind of the area of research for us for a number of years. And it's important also to recognize on this particular topic that, you know, we have occupational standards that generally cover industrial environments, especially for things like dust and certain of the chemicals that we deal with, but more particularly in what we consider the non-industrial environment. And this might be a classroom or an office setting. We really don't have those regulated standards on acceptable criteria for levels of exposure for some of these chemicals and particles. So we have to learn about this and make some of our best guidance in terms of what that exposure might be. So next, I'd like to share with you some of the research that we've done on quantifying what comes off of these 3D printers when they're operating and how they might affect your health. This is a shot of our laboratory where we do those studies. And until a few years ago, when we began these studies, there was not very much information in the marketplace about the impact of these 3D printers. And we actually started getting calls from folks in educational environments asking us, well, we've got these 3D printers operating, but we had a student who responded negatively with respect to a respiratory issue. Are there strange odors? Are these odors a problem for us? What should we do? And we realized the answers to those questions were not available at the time. So we set out to do this research so that we could really understand what was going on during the use of these 3D printers. So in order to do this, we knew that we couldn't do it alone because it was very complicated. So we chose some research partners. We teamed up with Georgia Institute of Technology, the environmental engineering folks there, atmospheric chemistry folks, because we knew that they knew all about measuring aerosols and they had all of the fancy equipment to allow us to do it. And then we teamed up with an organization called the Weizmann Institute of Science over in Israel, who were experts on understanding the toxicity of inhalation aerosols. And then we teamed up with the University of Washington, or Washington University in St. Louis, who understood how to take data and model the exposure trends for these aerosols. And then we teamed up with Emory University School of Public Health, Rollins School of Public Health, who were experts on really understanding the health impacts of inhaled aerosols. So it took a community and we put it together and then began the research to understand what was going on. So our research objectives were pretty direct. First of all, we just wanted to characterize what these particle and chemicals were that were coming off of these 3D printers while they were operating. What were they? What levels were they? How could you might control these emissions, and what might be the health impact for people that were exposed? So, and last but not least, we were hoping coming out of this research that it would allow us to establish a reproducible testing method so that we could get something out in the marketplace so that other laboratories could do this testing and that we could all start generating data that was comparative across different organizations. And potentially, we weren't sure, but we thought that this might lead us, if we could gather enough information, that it might lead us to developing a consensus standard for how you test these 3D printers and also establish emissions criteria for acceptable levels of chemicals and particles that could be emitted from them. So those were our objectives. And we set out by doing this using these exposure chambers, which this is a picture from our laboratory with a 3D printer sitting in it. These exposure chambers are something that are unique to our research capability that allow us to study products and understand what's coming off of them during operation. Also allows us to simulate hands-on activities while they're operating through various interactive ports. So what we found basically was that during operation, these 3D printers were generating a complex mixture of a lot of airborne particles and a lot of volatile organic chemicals. So most of the particles that we did measure were very small in size. Those are what we call the ultrafine particles. And some of the VOCs that we identified are known irritants, carcinogens, odorants, and even reproductive toxins, which means we have all of those coming off when these things are printing. So this means that we have a potential human health hazard. And we learned that this was particularly true when people were standing close to it with minimal ventilation. So a little bit of more detailed information. As I said, we found that the complex mixture of things coming off, the VOCs, which were primarily associated with the actual chemistry of the filament material and the operational parameters, how hot this filament was being heated. And we found overall that the total volatile organic chemical exposure for individuals could be more than 900 micrograms per cubic meter, which is about twice the amount allowed in our high performance building standards that we consider acceptable right now. On the particles, we found many particles in the ultrafine particle range. And I would say in general, more than 90% of the particles were in this very, very fine particle range, and they could reach very high levels. We typically measured up 10 to the 12 particles per hour, and most of them were nanoparticles, ultrafine particles, less than 100 nanometers in size. And for those of you that know particle chemistry, ultrafine particles present a major health concern. And it's one thing that we do get concerned about when we see that happening. So based on all of this research, we know that these were kind of the key elements that affect the emissions coming off, what they were, the levels of them, et cetera, were the actual printer itself, because different manufacturers of printers operate a little bit differently. We found that the filament, not only the filament chemistry, but the filament brand significantly affected the emissions. So a nylon filament from 2 different manufacturers could have different levels of emissions. And we found that the extrusion and build plate temperature had a pretty significant impact on the level of emissions coming off. So let's talk now a little bit about understanding the health impact of these emissions that we measured. So VOCs, we found 20 plus different VOCs coming off, and I indicated that many of them fall into these particular classifications. And over on the right, you can see some of the frequently detected VOCs: styrene, caprolactam from nylon, benzaldehyde, ethylbenzene, acetaldehyde. And some of those VOCs that are not commonly found in the indoor air, but that we saw contributed significantly by 3D printers were vinyl cyclohexene, caprolactam, acetophenone. And there were some VOCs that right off the bat, we knew that they exceeded current recommended exposure guidelines, things like formaldehyde and caprolactam. So we've continued to do studies on 3D printers, and probably our VOC list is up to around between 300 and 400 different VOCs now. So that list continues to grow based on our continuing studies. Health implications of these VOCs, formaldehyde definitely is a carcinogen as well as a strong respiratory irritant. Benzene is a definite carcinogen. Vinyl cyclohexene, which we found uncommonly identified in the indoor air, but almost always around the 3D printers, as a potential carcinogen reproductive toxin. And caprolactam, for example, is something we hardly ever find in the indoor air, mainly because caprolactam is a semi-volatile type of chemical. You don't see volatilized much into the air, but we see very high levels of that in the air when you use a caprolactam filament. So VOCs can cause all kinds of health issues, primarily in typical indoor air settings at the levels that we're dealing with. Most of it's related to eye, nose, and throat irritation, headaches, symptoms that are similar to flu-type symptoms with nausea and loss of coordination. And obviously, longer-term exposure can lead to concerns and detrimental impact on the central nervous system, cardiovascular disease, cancer, and a significant asthma trigger. Now, particle emissions, what did we find on those? And we studied these pretty significantly. We looked at particles, we looked at particle sizes, particle ranges, particle numbers, and pretty much in all cases, we found that majority of the particles that were being released, and typically over 90%, were in the ultrafine particle range, less than 100 nanometers in size. So how big is an ultrafine particle? Well, if you look at this slide, there's a human hair at 70 microns over on the left. And then in the middle are what we call fine particles, PM 2.5, which you hear a lot about today from an air pollution standpoint. But then if you move to the right, you'll see the ultrafine particle, less than 100 nanometers. And you really can't see it in relation to the human hair. So they are extremely small. So what does that mean? Well, that means that ultrafine particles can act as a gas. They get inhaled into your pulmonary system. They can get down low in your pulmonary system, they can transverse, they can actually get into the bloodstream and go through various membranes. And we know that ultrafine particles can actually eventually make it to the brain. So it is a genuine concern. Now, in addition to that concern, they also can be the cause of general irritation, just like VOCs, but we know that they are strongly associated with aggravation of cardiovascular coronary concern. And particle exposure in general, and especially ultrafines, we know are associated with premature death in people with pre-existing heart and lung disease. So it's very not good for these ultrafine particles to be coming out being emitted by these printers, but we do know that we have ways of controlling it, and that's the good thing. So looking at this, just to give you an idea of an exposure model estimation of what we measured in the laboratory versus real world conditions. And we've just shown you some standards that are out there. What's an EPA 24-hour PM 2.5 standard? And then the blue bar over on the left shows you what someone gets exposed to standing next to a 3D printer while it's operating in comparison to that EPA outdoor air standard. And as you can see, it's very elevated. And also, there's been a lot of work done at looking at particle exposure, especially coming from vehicular exhaust on roadways. And we have a general number. We usually see around 2 to 10 to the 11th particles per cubic meter next to highways. And this shows you that if you're operating a 3D printer, what you will get exposed to up close versus an office in comparison to what we're normally measuring on highways. So being up close to a 3D printer is essentially being like sitting beside a major highway in the United States. And then on the far right, we have the total VOC exposure level that is recommended for our indoor air quality in general, according to ASHRAE 189. And you will see the VOC exposure can be very high in comparison to that particular recommendation. So in general, we are producing exposures that are of concern and that can affect human health. Ventilation, and I indicated earlier, ventilation is a key element to controlling indoor air quality. And this slide just shows you for total particles and VOCs that if you increase the air exchange moving around that printer, you can decrease those particle and chemical emissions significantly. So ventilation is very, very important. Also, the number of printers that you have in a space can also affect exposure. If you have one printer versus four printers, you'll see the more printers you add, the higher the emissions go overall. And we have concern, especially in upper education, where we are creating a lot of maker centers that have dozens of these 3D printers in place. It means that they can produce a lot of exposure, which means we really got to take the care to understand that and apply the ventilation needs and mitigation needs that should be in place to protect the users. So overall, when we operate these things, we're creating a very complex mixture of pollutants. And one thing that I like to bring up when we're talking about health effects is that, you know, we study health effects chemical at a time, or particles almost, based on defined classifications. And we know very little about what happens when you put these mixtures together, where you have it all together and kind of this cocktail mixture of chemicals and particles and synergistic reactions going on, et cetera. We really don't know what's happening in that case. And because of that, we believe that taking mitigative risks to reduce exposure is a very wise thing to do. So 3D printer use in institutes of higher education. And Ryan, I think we're going to you on this one.
Yes, ma'am. Thank you. Well, Dr. Black gave you guys a bunch of great information here. I'm sure, like many of you kind of where I got involved in this, and I'm sure as safety professionals, we can all appreciate this in some extent, where you just sort of, hey, by the way, this is now under your purview. That's kind of how it happened for me at Georgia Tech, where it was like, by the way, your lab and chemical safety, yeah, we don't have anywhere else to stick 3D printers. Safety, we'll put it there. And that's kind of how I got involved in it. So that backdrop of information in terms of the research side and what's happening with emissions and all that stuff. I mean, we could, I think, qualitatively think about the fact that I'm sure there's a lot of nasty stuff coming off these things, but we don't know exactly what. And that's where, we really got joined up with a lot of the research that Dr. Black and Chemical Insights was doing. So with that, absolutely getting into, kind of our use here in not only in institutes of higher education, but certainly, as I'm sure you all can appreciate and recognize to some extent, it's going in everywhere. Manufacturers are using it for a number of technologies. If you have younger children, you're probably starting to see these things pop up in their schools. So, this is not really, I don't think, hyperbolic to say that 3D printer technology is changing the way we live. It is to a certain extent, and we're seeing it really, crop up all over the place. With that being said, there's a huge amount of these things in use, and I forget exactly where we pulled this estimated number. I'm sure it's something that that Dr. Black and Underwriters Laboratories looked into in terms of how many we actually have in use, but I think this might actually even be on the low side. I mean, I know, again, my own kind of microcosm perspective at when I first started seeing these things seemingly pop up like wildflowers everywhere at Georgia Tech, from makerspaces, research labs, to we were even getting some, kind of conversation that, hey, by the way, so-and-so's got one in their dormitory. And it's like, whoa, okay, I guess you can buy these things pretty much anywhere. And you pretty much can. If you do a quick Google search on 3D printers, there's a number of companies that are more than happy to sell you their 3D printer and take your money. So just something to keep in mind in terms of the amount that's out there, of course, and why they make them so easy for people to acquire. As it says here on the slide, I mean, most of them, you can get one for fairly cheap these days, depending on the size of the model and certainly what the type of feedstock is and all that stuff. But you can find one that fits on your desk in your office, or you can find one that, really will go in just about to fit in any spatial location. So specifically, of course, what are we concerned about in higher education? And of course, Dr. Black kind of touched on the background, a lot of this stuff. It's really about the amount that you have going in, what type of feedstock are they going to be using, who are the users that you have that are going to be using these things, what's their level of training, what's their level of understanding. And another big key component of this is, what sort of guidance are you getting from the actual manufacturer in terms of, are they giving you specifications for install? Most of the time, it's been my estimation that a lot of the manufacturers of 3D printers, they're pretty reticent to give you a ton of information about that, because it's almost like a liability perspective for them. For obviously, they don't know your specific spatial configurations. They don't know the level of education and training that your users are going to have. So they're pretty hesitant to give you a lot of specifics on that. But just one thing that you want to consider when trying to put those in, whatever your place of interest might be. And specifically, as we get into this, we're going to look at, to start off with, I'm going to go through a few examples here. And I'm going to kind of just set the table, because we're going to revisit these examples to most of these, and then a similar example, but a different setting as we get towards the back end of this presentation. So if you're starting to see the same picture again, you're going, wait a second, you already covered this. I'm laying a foundation for you guys right now as to kind of, again, the different sort of, at least in higher education, in my experience, where I've seen these. And certainly one thing that I want to hear from you all in the chat, and one thing that I want for all of you to maybe bring up in any Q&A topics that you might have, is how you're seeing this implementation go. Are you seeing it the same way that I did when I was at Georgia Tech? Or are you seeing it the same way that maybe other institutions that you've gotten feedback with and talking on the CSHEMA forum, or any other conduit for that matter of communication? So, as Dr. Black alluded to in one of her earlier slides, the maker spaces, maker areas, whatever you want to call them, we're seeing a lot of these pop up all over campuses, where essentially it's just this huge open area for undergraduate students, sometimes graduate students, sometimes faculty, sometimes just open to staff. Hey, if your card that gets you into your buildings works on this location, you can get in and use this, which is, kind of scary for a number of reasons that I'll get into here in a minute. But this sort of design studio, invention center, makerspace area is probably where a lot of you are seeing these things pop up. And again, this presents some really unique challenges to us, not only in terms of the amounts, but also who has access to them, and whether or not they're going into new build outs or renovated spaces. So next up on our list is going to be talking more specifically where you've got these makerspace type locations, but they're they're going to be maybe confined to a smaller audience. And in a lot of ways, that's a good thing, because then we do have more control over some of the variables that I just spoke about, where now we're moving from that open space where potentially anybody that has a card access to the doors to get into the building might have access to this space. We now can confine this a little bit more in terms of, we know the background of the people that are going to be using these, whether they're undergraduate students, graduate students, postdocs, staff, faculty, et cetera. We know we at least have some extent of knowledge in terms of what their use is going to be. So like in this specific example, this went into one of our aerospace engineering buildings, and we knew largely what they were going to be doing with these 3D printers. It wasn't going to be, oh, so-and-so wants to design a toy dinosaur for his little brother. We knew what they were going to be doing with these instruments. So it really gives you a little bit of an insight in terms of knowing the scope of what these things are going to be used for. The last example that I've got here is really more, and this is my favorite example in terms of your ability to be able to control the hazards that are associated with it. And that's when it goes into a research laboratory. And some of you guys are probably rolling your eyes at what I just said. What do you mean control stuff that goes into a research laboratory? That doesn't happen. Well, it does and it doesn't to a certain extent. I'm sure we can all appreciate the challenges that go along with that. However, the one nice thing of going into a research lab is that most of the time, the air changes per hour, as Dr. Black had alluded to in an earlier slide, and I can't reiterate it enough, kind of goes back to the old adage of the solution to pollution is dilution sort of thing. We generally have better air change rates per hour. We have engineering controls available to us. We have PPE available to us in most of our research laboratories. Also, very much more, with thinking of a even more refined scope of people that have access to this space more so than we did for any of the makerspace examples or the invention studio type examples that I just showed you, whether they be specific to an engineering school or they're open to your institute at large. So I think that this is nice because you have all those factors built into it, as well as, again, optimizing it usually for a very specific research purpose. Okay, so now that I've set the table of those examples, we're going to talk a little bit about some of the specific control pollution. How do we control the pollution that's coming off of these 3D printers? And most of you all are familiar with the hierarchy of controls. I don't want to go into this. Most of you as safety professionals have seen this a million times. You probably have it built into your one of, if not every one of the trainings that you conduct. But again, I think the key thing here is that, of course, we always want to try to make sure that PPE is our last line of defense, because there was a number of instances where in the past somebody would come to me and they say, we want to be fitted for a respirator because this is the type of 3D printer that we're using. We're like, wait a second, why? We're going backwards here, guys. We needed to look at some of the other things that should have come first before we started looking at PPE as our main way to control the safety of somebody using this. Now, again, I get from a real world perspective that you're not always going to be afforded that opportunity. A lot of times you are finding out about these things retroactively and you're kind of reacting as such and trying to figure out, oh my God, something's on fire, I got to put the fire out. And that's basically how you're dealing with this. So you may start at the bottom of this hierarchy of controls as it relates to retroactively assessing a 3D printer that might already be present on your campus. And for the mitigation strategies, I can't stress enough that if you're able to get in front of these proactively and you know about them, working with your design and construction team, your facilities team, your architects, whoever it is that helps design your new constructs or your renovated areas, to try to make sure that you're in good with them and that you're talking with the researchers coming into that area. You're talking with those designers, and whether they're like most universities are, they have their own internal design and construction team, and then they hire a lot out to professional engineers, and then of course the GCs and the subs that actually do the work to build these areas or renovate these areas, making sure that all those stakeholders are together and that you understand. And then you as a safety professional coming in and learning as much as you possibly can, given that information that's provided from one of those stakeholders, and especially the researcher that's coming in there. Where is this going? What are you doing with it? What type of feedstock are you using? And being able to then try to scope that into things like engineering controls and proper location for how all of this stuff is being controlled. Where's the storage for your filaments going to go? Are you using a metal feedstock of some type? Where's that going to go? Is it flammable? Do we need to think about all these things in terms of the setting that where this is going in? And certainly when you have that advantage proactively, it's advantageous, to say the least. When we're talking about printer selection, again, most of the time, a lot of the researchers are going to come, if it's going into a research operation, that is, they're going to come to you and they have a very specific model in mind of what they need for their operation. When it comes to the maker spaces or kind of the general use type areas, they may not have that idea in mind. They may be looking to some of the designers for guidance on this and saying, hey, we know kind of what we want to do. We kind of have an idea what we want to make available, but we're not sure. And so again, the one thing that you can do as a safety expert, again, is to try to throw your 2 cents in to say, hey, at the very least, even if you don't know specifically for sure what make and model you want to buy, look to make sure that these things are as reputable as they possibly can. So is there some sort of a third party, certification, or is it somehow verified by the manufacturer? Again, I kind of spoke earlier to the fact that most manufacturers, in my experience, have been very reticent to say things like that, but you want to check into those things and see if you can, figure out whether or not it meets any of that, or does it meet any of the ANSI, CAN-UL 2904 compliance? Are these all things that we can incorporate into our bidding process if it's scoped out into things that are potentially still on the table? So make sure that, again, if you're able to, you take that into consideration, as well as, is it an enclosed printer? Is it open to the air? Do we have other things available to be able to help us control those hazards? That's the main thing when we're talking about printer selection, at least from a safety perspective. And then filament selection. And I know that I think Heather had posted something in the chat earlier about asking, kind of what is the most dangerous type of filament or feedstock that you can use in a printer? And I'd really like to let Dr. Black address that more at the end. But of course, as she did already cover, and to some extent, there are different hazards associated with these different types of feedstocks. So if you can try to get them to work and build the same type of 3D printed model for whatever it is that they're trying to build with a lesser hazard, just much like we would use the substitution premise in a chemical, if we can accomplish that same goal with something that's less hazardous, let's push them to do so. So that's, again, where you come in as a safety professional to kind of throw your 2 cents in. And again, if the manufacturers are giving you some specific recommendations, make sure you follow that. And then, of course, again, purchasing the brand or the type that goes with the printer is key, because you don't know what sort of incompatibilities might arise if you try to start using something that's not appropriate for that printer setting. And again, placement, I can't stress this enough either. Depending on, again, whether or not you've got an area where you've got high occupancy traffic and things like that. Do we have a fire sprinkler system in place we're working with? And one thing I haven't yet touched on is a lot of these 3D printers they suggest, or the researchers or people using them will put sodium hydroxide or acid baths or something on the flip side of that 3D printed component so that they can clean it up and make it look all shiny and nice and however they want it. So there's other hazards that are associated with the 3D printer besides the emissions themselves that you got to think about. Location. Do you have local ventilation available to you, such as a fume hood, a canopy hood, something like that, where we can help kind of control all these things with respect to placement. And then this just goes to show you a little bit of a demonstration about, again, the pollution, solution to pollution is dilution kind of thing with air changes per hour and overall ventilation. Essentially, take home message here is the more ventilation you can push through an area where you've got a 3D printer or multiple 3D printers, the better it is in terms of, at least from a particle concentration perspective or a total volatile organic compounds perspective, and what we have in terms of what happens when you're not running that vent fan and whether or not you are running that, vent fan and what that looks like. So, if you're able to automate these things and not make it a user option, a lot of times that's advantageous, but of course it also may not be energy efficient. And those are things that you'll have to talk with your team about in terms of what you're looking at with regard to implementation for this type of thing. And then again, this just kind of gives you an overall schematic about, kind of your typical setup of a room. And of course, this is not a research laboratory, but if this is going into kind of a non-hazardous area, what would that look like? And what are the things that we need to consider and think about? Again, being close to an operating printer, Dr. Black already touched on this a good bit. So the further you can keep people away while these things are operating, the better. It's that proximity perspective in terms of, again, the closer you are to the hazard, the more likely you'll be to exposed, and whether or not you have a standard protective mask. Again, a mask, that term is so loosely thrown around now, but at the same time, again, an N95 may not be appropriate for controlling this hazard if indeed you can't control it through other measures. So you may have to look into some additional respiratory protection if that's the case. Hours of operation and makerspace type setting. Again, you may not have the luxury of being able to do that. A lot of those type of spaces are open to the public pretty much all the time. Or I shouldn't say to the public, they're open to the public on campus. So your students, your staff, your faculty, they may have some hours of operation, but certainly, again, you may see some of those operations they have people that will come in and they'll load something and they'll build something and let the 3D printer run overnight. If we can keep people out of the room while they're operating, that's certainly something to take into consideration while this is happening. And then again, if the 3D printer also requires any particular sort of cleaning operation to go with it, I haven't seen this too much in terms of the particular guidance that comes with your regular kind of ABS and PLA type filament printers. I know there is guidance there, but it's not quite as strict as, like, for instance, if you've got, again, something like that uses a metal feedstock like titanium, for example. So there may be some really, really strict recommendations that are there in terms of how you do that. Is it, do you use a HEPA vac? Is there some sort of a wet cleanup method that you can use or something like that in order to protect the atmosphere that's around, especially if that printer is somehow, if the emissions are somehow getting out into that area that surrounds it. So making sure that we keep not only the area clean, but also, again, of course, just good hygienic practices for your people is a key component of this as well. With reduced occupancy considerations, this is something that, again, we talked about it just a minute ago, and trying to, keep this in mind whenever you're designing something. Sometimes you're not always going to have the advantage of knowing what an occupancy of an area is going to look like, especially if it goes into that makerspace type setting that we've been referencing on and off. But this is one thing that's been a realistic consideration, obviously, since COVID's happened, where we've already had reduced occupancy considerations in a lot of areas, and whether or not that can be useful in terms of trying to control the amount of traffic that we have going in via some administrative mechanism, like, certain people only go in at these times or whatever, and you kind of have a shared, that may actually be helpful to us in terms of how we're able to get people away from these hazards a little bit moving forward. And whether or not we actually revisit full occupancy, or you're already revisiting full occupancy considerations on your campus, those are things that you'll have to take into account when you're trying to look at these spaces. And now what we're going to do is we're going to go back in and we're going to revisit some of the examples that I talked about earlier, and I'll try to wrap this up for you guys. But again, I just want to, with this first example that we showed with kind of the makerspace type setting, obviously, again, the main key variable here is the amount that you have and whether or not you were able to get in front of this. So, like, if you walk into an area and this is some area that they just decided they were going to stick 50 3D printers in, and they didn't do any particular renovation or preparations for it from a ventilation perspective, or making PPE available, or making administrative controls available, like we've talked about with regard to access and all that stuff, you might be in a bit of a pickle, because this is something that you wouldn't want to consider. You would consider this a high hazard area for a number of reasons. So, essentially in this particular example, thankfully, we were able to get in front of this. We knew that they were going to use this space for this, and the ventilation was adjusted as such. Now, if you're looking for some data to benchmark with for this, and you don't have something like this on your campus, and there wasn't something like this on our campus at the time that this went in, you kind of have to look to some other resources for that. And certainly Dr. Black can talk to some of that about what they have through Chemical Insights, as well as, again, at some of your peer institutions that may have facilities like this. What have they done to try to see whether or not this is effective? So really our most effective control in this case was just our overall air change per hour. And that's how the room was designed. Our next example, going back to the space that was very specific to the makerspace that was part of a particular school. Again, smaller space, not nearly the amount of 3D printers on the previous example that I just showed. We're probably talking somewhere in the neighborhood of, I think, 20, maybe not even that many were in this area, but still enough that we need to be concerned about it. And this also, the top picture is showing you a sodium hydroxide bath, which I touched on briefly, where a lot of these 3D printed parts are coming out of it, and then they're taking it into, here's our back room where we have our 3D, printed, our sodium hydroxide bath sitting up on top of a counter next to a sink, and really no other means to control it in terms of, there's some gloves sitting there. Are they appropriate? Probably not. What level of training does somebody have that goes into this? These are things that you might be able to control a little bit more with the fact, again, that this is very specific. And thankfully, in this case, and that when that part of it was discovered, we were able to do that and work with the right stakeholders to make sure that that piece of the training was considered. So again, besides control card access in this particular case, there was some other administrative oversight issues with respect to training that we needed to make sure that we got in front of as well. And the last example, kind of going back to the research lab example, and this is a different research laboratory than I showed previously, but we had the advantage here where We knew what was coming in, and it was dedicated users. We had like 3 researchers that were working with this particular 3D printer. We knew that because of the size of this, it wasn't going anywhere. It was tied into it hard ducted into ventilation. And we already had looked at a dedicated template design actually that down at the Delta facility in Atlanta, where they had a metal 3D printer that looked just like this that they were using to print 3D print metal parts for planes. So we had a really good basis to go off of in terms of our comparison for how we were going to control the hazards associated with this. All right, next steps. Dr. Black, I think I'm throwing it back to you for this and we'll wrap it up.
Okay, well, I think you probably have more questions than we provided information for, but we are continuing to research this particular technology. We're looking at the range of different technologies available. For example, we've just finished a study on SLA printing, because some of these printers that were originally in the industrial environment are now being reduced in terms of their footprint. They're getting smaller. And so people are now carrying them into classrooms and even home environments and things like that. So we are continuing, and we are actually doing work where we are monitoring the air quality in schools to get that data so that we can relate that data to what we're finding in the laboratory and make sure it's a one-to-one, and also gather data that will allow us to develop exposure models that can lead to recommended ventilation rates and that type of thing. So we're continuing to do that. And we're also continuing to look at the toxicity of the 3D printers. I didn't talk a lot about that before, but we did find in some of the preliminary data that these aerosols did demonstrate toxicity. And we are now continuing that work, exploring the toxicity of these aerosols using some in vitro exposure work with epithelial cells, et cetera, to understand really what is going on. So you will continue to hear more about this, or you can also contact us for more information. We do have a website, and we have a page actually dedicated to 3D printing, where we have all of our current resource materials, which are guides for operating these safely, specific information on the research. We actually have an online e-learning module that takes you through understanding the hazards. We have a poster which is on the left-hand side, kind of the 10 ways to promote healthy indoor air quality while using 3D printers. So you can find all of our materials there, and they are open, transparent, free to all of you guys, and you can contact us at any point in time with any particular questions. So we are trying to engage some higher learning environments where we can go into their maker centers and gather some research data. So if anybody's interested in hosting us there, please let us know.
Awesome. Well, we definitely do have some questions that have come in. I know we don't have a ton of time left, but with the time that we do have left, I'd like to start addressing some of those. So one that came in for you, Dr. Black, while you were speaking, Nancy's asking about some of the sampling strategies, in particular that you were using for research, and what sensors or air sampling strategies did you use in the exposure chambers that you were referencing earlier?
Yeah, well, we have some fairly unique capability. We have online real-time aerosol monitors that measure the particles, the sizes, the distribution. You know, one of the instruments is called a nanoscan that actually takes that aerosol and measures all that information about the particle sizes. And then we have unique capability on collecting all of the VOCs and doing a scan and analysis of those for using a database for indoor air quality that has a couple thousand different VOCs in it. So I think on our website, we have some technical briefs that talk about those available technologies for doing those measurements.
Awesome, thank you. And then Heather was asking earlier too about, can you speak to which filament materials are the quote safest? And I think you addressed this to some extent, but I don't know if you want to elaborate on that a little further. You
know, the one thing we found, the ABS type filament, just because of more of the petrochemical base that it is, gives off a lot more chemicals. And the PLA is good in terms of release of very minimal chemicals. So it produces probably the smaller amount of chemical exposure. However, in our toxicity studies, we're finding that PLA is showing stronger toxicity. So, I think PLA has kind of become the default filament of choice just because of the lowest emissions, but the jury's still out on the toxicity of these aerosols.
Sure. There's been a lot of questions that have come in too, guys, about how you can access this presentation retroactively. Katie and CSHEMA Central Office will make it available in the archive section so anybody that wants to watch it after the fact that wasn't able to attend certainly can. There'll be a post survey that's coming out after too that will probably also be coupled to some information about how you can access this presentation after the fact. So for anybody that's asked that question, we'll make sure it gets out to you in some capacity. I can assure you of that. Another question for you, Dr. Black, I think this is definitely more in your wheelhouse in terms of based on what you found in your research is, what do you think can and should be done in spaces where very young children are present?
Well, I think very young children obviously are of concern because exposure of these sorts of pollutants to children creates a more significant hazard than exposure to us as adults, just because of their ability to breathe faster and because of their developing biological system. So, definitely we should not have children standing next to 3D printers, and we need to make sure we put some of those control measures in place with the ventilation and some of the new filtration strategies that are being developed that actually extract those emissions away and prevent exposure. So that's also part of our research, and we have some information available on that, but you do need to be careful with small children.
Yeah, absolutely. There was a question that came in from Allison too, regarding, is there a resource document that can be referenced to determine how much ventilation / number of air changes are needed for spaces based on number of printers and type of 3D printers? And my answer to that, I'm sure Dr. Black would have more of a technical perspective on that, is there is no black and white answer to that. There are some guidance documents that are out there from certainly from ANSI and ASHRAE and stuff like that speak to the ventilation aspect, but as far as giving you a black and white, here's the number of printers that you have, and here's the type of filament that you're using, and this is the type of air change, or this is the amount of air changes per hour that you need based on the spatial square footage or cubic feet. I don't think that exists. At least I haven't seen it. I really think that is an effort between you as the safety professional, again, your architects and engineers, and everybody kind of coming together to try to parse out that information the best they can. And Dr. Black, I don't know if you want to add anything to that.
No, I think that's true. And I think, again, that's part of the research and what we're trying to learn from some of the in-school studies that we're doing.
Okay, awesome. Another question that came in, and I know we're up against it here, guys, but we'll try to get in as many of these as we can. Have any of you developed generic training on 3D printers for your institution, or is all of your training managed locally per room printer type? And I'll address that obviously from the higher education perspective. We did not have any specific training that was offered that was that formal anyways, like a PowerPoint presentation or something that kind of had a stock set of information. What we would do is kind of more to the latter there, which is was kind of managed locally per room and printer type. At Georgia Tech specifically, we had a 3D printer info sheet that was on our website. And then what it would do is essentially clue people in that, hey, if you're thinking of getting one or you have one and you haven't had us come in and do an assessment, or you need to see what we need to do from a safety perspective, make sure you contact us and give us this information. Where is it located? What filament type are you using? Who's using it, et cetera, et cetera. So I would just suggest that that's probably your best course of action, because again, it's really hard to try to get a generic presentation that will speak to all the particulars of each 3D printer and the location that it goes in. Dr. Black, did you want to say anything or add anything to that?
Yeah, that's good. I encourage everyone to go look at all the resources we have available, safety tips, et cetera, so that can give you some information that can maybe help you if you want to put your own guidance together.
Okay, awesome. And the last question, a lot of these were comments, and I know, again, we're over, but the last question was really specific to bioprinting and whether or not, I know certainly I did not see a ton of these in my time at Georgia Tech, and I have not seen any so far here at my time at UT Southwestern, but I know that is an emerging technology that's popping up everywhere for people. And Dr. Black, I don't know if you have any experience with this and have done any research into this. And
no, we haven't done any studies, but we do know there's some universities that have units that are set up that are starting to do a lot of this. And it'd be good to get some measurements and see what's going on.
Okay, excellent. Well, again, guys, thank you all for your time. I know we ran a couple minutes over. I really appreciate all the questions and comments that were in the chat. I think this is helpful. Katie's posted some stuff in there in terms of the survey and where everything will be made available for you all, as well as for anybody that wasn't able to attend. So please make sure that they're aware of all of that. And just thanks so much for attending, and keep your eye out for future professional development committee webinars and things that we're organizing, as well as all the other things that the communities of practice and the other committees in CSHEMA are doing that are usually posted with quite a bit of advance notice on our website. And make sure that you're patronizing all of our great CSHEMA networking customers and attending their stuff and getting useful information that you can hopefully take back to your institution and put into some sort of action. So thanks again, everybody, for attending, and please feel free to reach out to us after the fact with questions.
Thank you.
Have a great day, everybody. Thanks, Dr.
Bye.
Black.